Spasibo. Pleased to be here. I'd like to tell you about digital fabrication and fab labs, and I'll do that in a few stages. The first stage is to tell you a little bit about the research. The second stage is to tell you about how the Fab Lab networks started, and then I'll tell you about what's grown from that in the business and education and research. This will be a high-level tour. I'll give links to everything I'm presenting for you to do more detail afterwards. So I direct the Center for Bits and Atoms at MIT. And this is interdisciplinary. It's many different disciplines across campus working at the boundary of physical science and computer science, hardware and software. And in that research range, one of the core ideas that's emerged is telephones were analog. They got worse with distance. We now have an internet. Computers were analog. This was the last great analog computer at MIT. They got worse with time. We now have PCs. But machines to make things were analog, and we're now making them digital. And that has a much deeper meaning than you might realize. And so what I want to explain is what that transition means. Initially the research, and then the impact. So these are among the most advanced ways manufacturing is done today for composite airplanes or 3D printing or chips. But you can trace all of these back to this. In around 1950, MIT made the first milling machine controlled by a computer. And a lot's happened since, but it's really the same process. You move a head around. In 1950, it would cut. Now you can print, but there's no information in the materials. It's all in the computer. Now, compare that machine to this process. If you look at this process, this one has a lot of benefits. If a child plays with Lego bricks, they don't need a ruler to measure the position. The bricks have coordinates, unlike the milling machine. The Lego corrects errors, and so this tower of bricks is more accurate than the child. That's not true of the machine. The milling machine, errors accumulate. And then when you're done playing with the bricks, you don't put them in the trash. You take them apart and use them again. With the milling machine or the 3D printer, you put it in the trash. So in many ways, this is a much better process than this process. We're pursuing that idea in stages. In 1950, computers controlled machines. We're then developing machines that can make machines. Then we're putting codes into materials, and we're ultimately putting programs into materials, is the pathway to digitizing fabrication. So I'm going to go through those stages. These are some machines we've made at MIT that can make their own parts. And this is part of a project not to make just one machine, but to make parts that make it easy to make many machines. So this one extrudes, this is multi-axis machining, this is printing, this makes circuit boards, this makes molds. It's a set of parts that makes it easy for machines to make machines. Now, as part of doing that work, traditionally you design, then you make a path for the machine, then you control the machine, and then you talk to the machine. It doesn't make sense here because everything's happening in one time. And so as part of the work on these machines that make machines, we've had to re-implement all of the internals of engineering workflows. So this, I can tell you more later, but this is a very interesting CAD tool that runs in a web browser, and it represents objects as, for the experts, as a mathematical satisfiability problem that's then solved with a compute server. There's a very interesting architecture for the CAD. Then, instead of having a file you send to the machine, we have virtual machines in software that talk to computer networks that run real-time machines. And so those are just some of the pieces of the technology to make machines that make machines. Then, with those machines, we're then starting to make things that look like this. This is now a machine where instead of cutting or extruding, it assembles. And so these are tiny parts that you can, in this case, use to build electronics. So instead of etching a circuit board or extruding it, you can assemble it now with all the properties of building it with functional materials, building it in 3D, building it reversibly. So this is a discrete material, a digital material. The idea for that design actually came, in the back working is my daughter Grace, and she and her brother invented a construction system that was the inspiration for the design of these materials. And we've since gone on to study, this is the material science of discretely assembled materials, showing with the pattern you assemble them, you can tune the properties of the materials, not by mixing different chemicals, but just by the code of their construction. These are part of a CAD workflow to take a design and decompose it into discrete parts and then make an assembly sequence to build it. And then this is a very interesting version where with these discretely assembled digital materials, we're making carbon fiber composites. And it turns out these are the world's lightest and strongest materials with implications for things like the future of aerospace. We're looking at making large-scale aerostructures this way. So I started with machines that make their own parts, then started looking at discretely assembled materials. Those materials still have a machine that places them. The step after that is we're looking at materials that can reconfigure themselves. So this is a workflow that takes a 3D design and turns it into a 1D code that folds into an arbitrary three-dimensional shape. So now instead of the machine assembling the parts, the materials themselves contain a code that assembles into the shape that you want to make. And then we're working on versions of that with proteins, with clusters of small atom clusters, with droplets of fluids, with robots. Here's a robot that can turn into any shape, a part of a robot that can become any other robot in effect. And so here we're looking at materials themselves that can change shape. And ultimately, where this research is leading is to an idea that's 4 billion years old. This is the protein, the ribosome, and it builds the proteins in your body. You're full of molecular machines. There's motors that move your muscles and sensors in your eye. And the way they're made is based on everything we think of as modern computing. So a messenger RNA brings a code to the ribosome. It's designed like a modern code. And then amino acids are assembled, just like the micro Lego I showed you, that builds a protein. And the key point is, the computer isn't controlling a tool. The computer actually is the tool itself. And the program isn't just describing a thing. The program itself is a thing. The crucial distinction is the information is in the materials itself. Now that may sound semantic, but you wouldn't do a video chat with the US from here over an analog phone call. Of course you'd use the internet. And you wouldn't carry around an analog computer in your pocket. Of course, you carry a silicon chip. And the crucial distinction is the digitization. What Shannon and von Neumann taught us is it gives you an exponential reduction in error for a linear increase in the system, which means you can make things work perfectly even though the parts are imperfect. So you understand that for communication, you understand that for computing. Biology discovered that 4 billion years ago for biology, but manufacturing hasn't yet done that. So the deep meaning of digital fabrication is this research on how to actually put information into materials itself. That's the research roadmap where we're heading. And where it ultimately leads is, in Star Trek, there was a replicator that could make anything. And that's what we're trying to create. We're trying to make a replicator, but it's based on coding the construction from atoms on up by putting information into materials. And we think that's about 20 years away, 20 years of research to get to that. Now, to do the research I just described, we put together a facility with machines to make anything on any length scale, tools across sizes to scan things and produce things. And then the early beginning of the Fab Lab project started with, I taught a class called How to Make Almost Anything. And that was just how to use the machines for research, but I was overwhelmed with students desperate to take it who just wanted to make stuff. And so they did projects. Like Kelly was a sculptor, not an engineer, and this was her project.
Hi, I'm Kelly, and this is my screen body. Do you ever find yourself in a situation where you really have to screen, but you can't because you're at work, or you're in a classroom, or you're watching your children, or you're in any number of situations where it's just not good? Well, screen body is a portable space for screening. When a user screens into screen body, their screen is silent. But it is also recorded for later release, where, when, and how the user chooses.
So that was her project. This was a web browser that lets parrots use the internet. This was an alarm clock you wrestle with to prove that you're awake. This was a dress that had sensors and spines, and it defends your personal space if somebody comes too close. And so these were all projects students did in the class. And you may view them as just silly, but if you think of them in the history of computing, the leading computer company in the birth of the modern era was Digital. And the founder of Digital said, nobody will have a computer in the home. And Digital is now bankrupt, and you have a computer in the home. But the point is, it's not in the home for inventory or payroll. It's to listen to music and talk to friends and do personal things with the computer. And so the way you can understand these examples is digital fabrication leads to personal fabrication. And the purpose of personal fabrication is to make not what you can already buy, but what you can't buy. It's personal expression in technology. Very parallel to the history of computing. And so if you line up the history, there were mainframes, and that's like the big machines for manufacturing. Then came mini computers. This is a picture at Bell Labs of the operating system Unix being invented. And all modern operating systems came from this moment. The computer in your pocket is based on this. And this is when a computer became small enough that it didn't have to be used by a whole corporation, but a group of people could use it. And so video games, email, word processing, all of that happened here. And that's analogous to the Fab Labs that I'll talk about. Then came hobbyist computers like the Altair that weren't for mass markets, but were for hobbyists. And many of the computer pioneers began with this. And then we finally got the PC. The lesson from this history is the internet, all of the things you do with a computer didn't happen after the invention of the PC. They happened around here in the mini computer era. Computers got faster, better, cheaper, but the invention of what you do with a computer happened at this point in the history. And so now if we line these up, the Fab Labs are the cost and complexity of a mini computer. In 20 years, they'll fit in your pocket, but you don't need to wait 20 years to figure out what to do with digital fabrication. Then the machines that make machines are like the hobbyist computers, and the research is leading up to the personal fabricator. So what's in the Fab Labs today is not where the research is heading. The research is heading towards merging all the machines into one and building with intelligent materials. But even when we're done all of that, the applications are something you can already do today. So where the Fab Labs started is our facility at MIT was paid for with a lot of tax money. And so the National Science Foundation asked us to show social impact, show what is it good for. And we thought it wouldn't be too exciting to just make a website. It would be more fun to give people the tools themselves. So we put together a lab that was in between the research on campus and where it's heading, and we opened just one, and by accident, they spread all around the world.
Searching solutions for the world we share. Principal Voices in association with Shell.
We've had a digital revolution, but we don't need to keep having it. We can declare success we won. What's coming now is the digital revolution in fabrication. My colleagues and I started teaching a class called How to Make Almost Anything. And the idea was just that. It's a program looking at how the digital world relates to the physical world. And one of the core things coming out of the research is the idea of digital fabrication, making the Star Trek replicator, an assembler that makes anything you want by building the atoms on up. This is designed when you put in the millions of dollars of equipment at MIT are like the mainframes of digital fabrication. We can make anything you want using those tools. In 20 years, we'll make it so you can have it in the home. The Fab Labs are in between. They spread all around the world, letting ordinary people create technology, from South Africa to the north of Norway, and from rural India to inner city Boston. Instead of spending vast amounts of money to send computers and energy and communication around the world, you can spend much less to send the means to create it. Energy, communication, computation, just to say the words, they sound big. They're being tackled as billion-dollar mega projects top down. Fab Labs is tackling them from the bottom up. We're just finding so many people with such interesting inventions and such great ideas. Sharing that is where I see this going.
So all of that was an accident in that we opened one in Boston, then there was a strong connection to Ghana, and that led to a lab. This is Sekondi Takoradi on the coast of Ghana. There's a strong connection from there to South Africa. This is in Soshangovi outside Pretoria, essentially a shanty town. Rural Indian Pabal, Afghanistan. We didn't have a project to open these around the world. Our plan was just to open one. But every time we set one up, somebody else wanted one. And it was pulled by a divide, a digital divide, but not in information on the screen, by people who wanted to interact, measure, modify the world around them. And again, we didn't have a plan, but the way the labs used started with just kind of empowerment, informal learning, and then it turns on to hands-on education. This clip was done when we opened a lab in Ghana with essentially some street kids who came in off the street, and we're very excited. And then we were designing a sensor circuit board, and there was a young girl who wouldn't leave the lab the day we opened until she could make it.
My name is Valentina Kofi. I am 8 years old. I made a stacking board.
So she had made that by precision machining. She had just learned surface mount rework. She's about to load microcode in a microprocessor. I didn't do all of that till I got to MIT. I suspect many university students here can't do that. So this 8-year-old girl in a Ghanaian village isn't just kind of catching up. She's skipping over how certainly I learned technology. And then the lab started tackling a range of useful problems. So nobody's in charge. Nobody really runs this, but they've been doubling every year. There's about 100 now. There's about 100 planned. There's a base inventory. And if you're interested, I can tell you much more about this. But there's a set of tools that lets you do 2D design, 3D design, hardware, software, molding, casting, printing, embedded electronics, make complete integrated functional systems. Initially, I thought we would just throw this out when we're done the research, but instead what's happening is the inventory slowly evolves as the technology evolves towards the goal of a lab that can make the lab. But all the labs share these capabilities so that anything you design anywhere can be made anywhere, so that people and projects can be mobile. And then the community has grown. There's a meeting where all these labs come together that began in Norway. It went to South Africa, US, India, Amsterdam. Last year it was in Peru. Next year it's New Zealand, Japan the year after that. And so this has become much too big just for an outreach project. So from MIT, we're very involved in the technical roadmap. But what's growing is a foundation to help provide operational support, funds for businesses, academy for classes to keep up with the growth of the network. So to give you some examples of labs around the world and what they're doing, this is a fab lab at the University of Illinois, and they're surrounded by farming. And they used to do what's called in the US agricultural extension, where they set up stations to help the farmers. They're now using the fab lab to do technical extension, to do technical outreach into communities around them. This is a lab in Maine at one of the most revered places for artists to do traditional arts and crafts, things like blowing glass or materials like that. And there they use the fab lab to do things they couldn't do with other materials. Like an artist was struck by the light on the ocean in Maine. And so they used the fab lab to turn that into a 3D model that was then used to cast glass, so the glass looks like the ocean in Maine. This is a fab lab in Amsterdam. In the middle of Amsterdam is the Waag, the Way building, the customs house. And for decades, it's been abandoned. One of the most beautiful, important buildings. They didn't know what to do with it. Now there's a beautiful fab lab right in the middle of Amsterdam. And they're doing classes, they're creating businesses, they're making lots of practical projects. So if you're in Amsterdam, making a foosball table is very important. But here it can be custom, so you design the table. And they made this one where one team was me and one team was Darth Vader. So Darth Vader can play me in foosball. And you can design and build the electronic scoring and all of that as a complete project in the Fab Lab. This is a lab in Manchester, United Kingdom. This is where the Industrial Revolution started. At one point, they had 3/4 of the world's mills. Now all the industry has left. They just have some football teams, in fact, with Russian owners. They've lost their industry. And what they're doing now is they're working on a new industrial revolution, where in this industrial revolution, it was based on owning the means of production. You own the factory. With digital fabrication, the means of production aren't scarce. Everybody can produce. Instead, what you do is you go to market not by mass producing, but you ship data to go to market, and then you produce products on demand. So you can design something anywhere in the world and make it anywhere in the world. And the business becomes a network rather than a factory. It's a very, very different business model. Now, one of the questions that comes up often is, if anybody can make anything anywhere, how do you protect the intellectual property of a business like that? And the answer is you can't. Patents work only if you can identify who's infringing the patent. And so we patent research we do that involves big machines and has a barrier to entry. But we don't patent technology in a fab lab because anybody in a fab lab can infringe your patent, and you can't serve a summons on Earth. You can only protect IP if you can identify infringement. And this is exactly what happened to software and music. When MP3 players appeared, there was an attempt to protect music with digital right management, and it failed. So the DRM, the digital rights management, was removed, and instead what succeeded were platforms that made it easy to buy and sell music. The same thing happened with software. There was with apps, there was an attempt to protect the software. That failed. What succeeded were markets that make it easy to buy and sell the software. So in this world of digital fabrication, what businesses need isn't patents. What they need is income. And the path to income is making it easy to buy and sell designs. But it's a very different model from the intellectual property you use in big businesses. This is a lab in Barcelona where artists and architects and designers thought the engineers were getting it wrong, so they wanted to control technology. And for example, they did a beautiful project for the last solar decathlon in Europe. They made a solar house, and they made this the same way you make a playhouse, but now they're making the playhouse full size. And so they made a complete solar house as a project in the Fab Lab. So they made the house, controls, and all of the furniture, now doing rapid prototyping on this giant scale. And in turn, something really surprising has happened there, which is the team that runs the Fab Lab in Barcelona now runs the city. The mayor, the deputy mayor, the architect, all have ties to the Fab Lab. And the connection is, in Barcelona, or in Spain, there's 50% youth unemployment. Terrible economic opportunity. Meanwhile, they buy products that come in ships made far away, and they pass through the city, and then they fill trash dumps. And so what they're trying to do in Barcelona is make the city technically self-sufficient. It used to be agrarian, then it had a city wall to keep out invaders. Then it invented the modern notion of urbanism. Now what they want to do is, instead of bringing in products and producing trash, they want the city to be connected globally for data. So information comes and goes freely. But they want energy and food and products to all be local. So instead of those coming from far away, They want the city to produce what it consumes. And so they're working on filling the city with fab labs as a crucial part of this urban planning, because they want the city, when you want furniture, you don't go to IKEA, you go and design custom furniture. When you want consumer products, you don't go to a store to shop far away, you produce them on demand. And there's really a very interesting opportunity for the skills and jobs that they've been sending far away to come back to the city. But you can't do it by disconnecting. For knowledge, they have to be connected globally. Data comes and goes, but the products are done locally. So the whole city is becoming a grand experiment in urban planning around digital fabrication. This is a lab in Afghanistan that in turn has been looking at infrastructure.
Now, a story about MIT students who helped build a wireless network in Jalalabad, Afghanistan, out of junk. They call it Fab 5. It's a mix of Wi-Fi and Fab Lab. Students at MIT Center for Bits and Atoms have created fabrication laboratories, or Fab Labs, across the globe. Fab Labs are like community centers with machinery and computers that the public can use to create things. The goal is for the community to use and develop technology that addresses their specific needs. And here to talk with us about the Fab 5 project in Afghanistan is MIT graduate student Amy Sun. Welcome to the program.
Thanks, Robert.
And so she goes on to explain one of the biggest needs was communication infrastructure, where ordinarily that means $1 billion investment by a telecom provider. Here they use the Fab Lab itself to make data networks, to make bottom-up community internet. And it had a very interesting dynamic where people used to fight over who get access to resources. Here you didn't have to fight because you produce the network in the lab. The users can extend the network. So now they're starting to do things like building large area community infrastructure as a grassroots project. Then came the people. This is a Fab Lab in a apartheid-era township in South Africa. And Chapiso here was following my classes at MIT using the lab. I didn't realize that, but she was doing all the work of the classes with the lab. This was a young boy in a Fab Lab above the Arctic Circle, the same sort of thing. And so we had a problem that students were learning the skills and then like falling off a cliff. They were so far ahead of local schools, there wasn't a place for them to go. And so we started teaching classes in a Fab Academy. And the idea of this is, if you think about it in computing terms, MIT is kind of like a mainframe. You go to MIT for processing. Distance learning, like MIT's courseware, is like connecting a terminal to the mainframe. There's still a central hub, and then you plug people in at a distance. In the Fab Academy, it's a very different model, where students have peers in work groups in the lab with tools and mentors. Then they're linked by video and online content. So we teach classes where the lectures go all around the world, but instead of students being isolated, they're in linked groups. And so the campus itself is a network. It's a networked education. And so we're using this to teach classes in principles, applications of digital fabrication, and expect over time that'll expand to more classes that can be taught that way to build the educational infrastructure. This is a wonderful Fab Lab in DC, Washington, where it's in a mixed neighborhood, but at the end of the street is the Capitol, which is in fact, what is the building that this is? Yeah, that this is modeled on. And sites like this are leading to very interesting legislation. This is President Obama visiting one of the labs, and it led to this very interesting bill in the last Congress.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress. But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or for part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives which supports the goals and mission of the National Fab Lab Network as in the best interest of our people and the best interest of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have the chance to visit Neil and see the progenitor of all fab labs myself, and to work with the people in my own congressional district in Illinois who are planning to create their own.
So the idea of this legislation is, like you in the US, we have national labs that are billion-dollar sites. They're very expensive and often struggle to impact the communities around them. And so the idea of this was to take the network of labs and consider it to be a national laboratory made from community laboratories as a new way to think about the infrastructure for research. And so in each of these areas, the biggest surprise for me is I thought the research was hard. That's progressing well. But if anybody can make anything, it means that the usual splits of academia, industry, research, education don't make sense. This cuts across all of them, because it means by this linked global network of local labs, cutting across them, you can use it to create businesses, you can use it to teach classes. It really it's a very different way to think about the organization of each of those functions. And so in many ways, the project isn't what I thought, which is the technology that's progressing. It's asking, how do you live, work, and play with this technology? The technology gets better, but these questions about how you make businesses that are networked, how you teach classes in these distributed networks, each of these things, those are analogous to the inventing the internet. The building these new sort of organizational models is really the grand project. And that's what we don't know how to do. That's what's exploding around the world while at the core the technology progresses. For the World Economic Forum in Davos in January, we set up a Fab Lab right in the Congress Center. And this is the meeting where heads of state and CEOs come. And it was an amazing experience because the political leaders and the business leaders at this meeting were very depressed. The euro is in trouble. There's lots of fights between countries. You know, all the things they're responsible for were kind of a mess, and they were depressed and didn't know what to do. But the lab was full of excitement of people working not from the top down, but from the bottom up. All sorts of NGOs and community groups and educators and activists who were finding solutions to their problems with this technology rather than relying on them from above. So in many ways, to take the Barcelona example, Barcelona is kind of giving up on both Madrid and Brussels and saying, they're not going to take care of us, you know, we're going to solve our problems and in a sense become autonomous. And so the technology for digital fabrication, not in isolation, but connected to digital communication and computing, leads to a very different model for how you address these fundamental problems of employment, business incubation, education, that rests much more on empowering people to solve problems than on making big investments in top-down solutions. And it rests on what we're finding all over the world, and I'm sure we'll see here. A place like MIT can fit a few thousand people. The world has a few billion people. If even only 1 in 100 are the most inventive people in society, It means there's huge numbers that just don't have a chance to come into formal educational systems. And even more than that, the most inventive people tend to not behave well. They tend to be odd. They tend to not quite fit. And one of the strengths of driving this project is these labs provide a place where inventive people like that fit, where they can be inventive and not be limited by the rules of what they're supposed to do. So technically, the Fab Lab project is this roadmap of machines that make machines to codes and materials to programmable materials. The real goal technically is for the lab to make the lab. But it's grown into a global network, linked, that's really tackling, revisiting education, business, employment, all of those things by using this evolving window of technology today to address those problems. It's messy, it's chaotic. Nobody's in charge. It's a linked network. We're building capacity to help support it, but it's been growing by leaps and bounds. And we look forward to working with you on labs in St. Petersburg, across Russia, and around the world. So with that, there's background in these books off of my site. I'll share with Igor the link for this presentation, and then I'll be happy to take questions and discuss this. Thank you.